Good morning, everybody. So it's my pleasure to announce today the speaker of our seminar. That's Ami Abbas. And the title of his talk is Multiphysics Modeling for High Brightness LED Light Engines. Now, Ami Abbas is an alumni of our university because he made his PhD in 2014 in the group of in Elis department in physical electronics, and that was about the light absorption enhancement for solar cells. That was with Professor Burgelman and Bjorn Maas. So after finishing that, he went to KIT and in Karlsruhe, and there he started working on the absorption of light, how to create surfaces that absorb the maximum amount of light. Now, as he writes in his bio sketch, in 2018 he decided to look at the problem from the other side and to go to Lumileds. Lumileds is a company that is making light-emitting diodes, and there, of course, they want to generate as much light as possible. Now there is an engine that creates photons, but another problem is how to get the photons that are created out towards the viewer for useful applications. And I think this is going to be the topic of his talk today. In fact, gallium nitride LEDs were invented a long time ago in the 80s and 90s of last century. And there was also a Nobel Prize in 2014 for this invention, and it has changed the world of lighting a lot. So I think it's time for me to give the words to Aimi. I'm very curious to what he's going to tell us about Lumileds, a company based in Aachen, Germany, not so far from us. Okay.
Thank you so much, Christian, for the kind introduction. Hello, everybody. I'll be giving this talk in Lumileds. Thank you, first of all, also for the NB-Photonics group for inviting us to come here and talk about the research work we do in Lumileds. So basically, the content of our the talk will be in two parts about LEDs. What are they used now, and what is the future of these LEDs, and the modeling work that goes into these LED devices that what we are working on right now to produce high-end LEDs and what we are working to improve on. Now, so the first thing that we wanted to say that as years go on, LEDs is becoming more and more efficient, and they're becoming more and more brighter. They come in different size and shape over here for different kind of applications. Of course, as a year goes on, we always want to be able to increase the efficiency of LEDs in all the different colors. And even for an example over here, we want to use them for different kind of lighting, and different kind of applications typically require different kind of LEDs, and we have to tune a lot of things. Sometimes going as bright as possible, as efficient as possible, but at the cost of a bad spectrum is not so interesting for different applications. And sometimes we have to consider that the customer requires a particular radiation pattern coming out of the LEDs instead of just a simple inversion, and they are willing to accept the cost of, okay, they're going to be less light coming out, but at least when light comes out, it comes out the way you want it, and things like that. A lot of complexity comes and introduce additional requirements in how the LED should be designed. That gives a lot of opportunity and interest in engineering these LEDs and introducing different kind of components to meet those requirements. Sometimes these components are nanophotonics components as time goes on, and sometimes it's simple geometrical optics components. And And these range of applications is so diverse right now. It's not just simple lighting. There's lights that basically is used to as sensors for self-driving and signaling of semi autonomous vehicles. Oops. So and also light for sending data in internets, for even light just used for water purification, for biometrics, and all these other applications. They require quite a specific uh, type of emission, and there are challenges in each one of them. And our basically Lumileds goal is to produce the LED required by our customers that would fit to these applications. So essentially, Lumileds, you perhaps won't really heard of us so much from the direct customer side, because our main business is basically business to business. But um, most likely, even though we cannot really say which one, your cars might be using our LEDs. And also, you're most likely some of your smartphones are using our LEDs as well for the flash and for the facial recognition sensors. And we have basically a vision that is going forward, particular with regards to how the LED usage, the light usage in the automotive industry will go forward from this. This is actually some video of ours that we have over here that is set to impress customers of what will happen in the next 5 years, perhaps, in the usage of lighting uh, in cars. So it's not just headlamps anymore. We want to have it really to enhance customer experience also in the cars, where the LEDs are used to give additional signals to the people surrounding the car, so that they know how the car will go on and how to interact with the cars. Because this is especially of more importance going forward. We think as the progress in automatic self-driving cars are going, because there will be a need for these cars to interact with the surrounding people, and the people need to know how to interact with these cars that might be self-driving without uh, without the a person being inside the car sometimes. And even further going forward, perhaps this is actually just a future expectation of how these cars might be used. It might be there's going to be a more uh, fancy usage of the windows over there, like you see, that requires basically LED products as well to be used in these things. So we envision an automotive industry that becomes more interactive, basically with society at large. Pizza delivery. I mean, that's really the best application I could think of LEDs. And I want to go to a more specific possibility, because I mean, different applications, there's going to be a different future roadmap, but I wanted to make you interested also in what's basically the future of headlighting, for example, in LEDs. Uh, so for headlighting, currently uh, most cars basically just use it to illuminate the road. And as you if you know a little bit about the automotive industry, it's very stringent requirement of, yeah, the light must be this much, there's must this much glare, and it must have this kind of field of view. It must not produce so much uh, stray light, and it's definitely it cannot accidentally blind the driver and all that, which complicates stuff. And however, there is still room for a lot of within the set of regulations of safety in the road to improve the functionality of this headlighting. And one of the ways to do that is to essentially digitize the headlighting uh, possibilities in cars. So instead of just relying on one or two lamps to light the road, as time goes on, we think that it's going to be more important to have a really digitalized headlamp, for example. And first generation, we think it's going to be just a simple uh, ADB matrix, what we call it, just a simple LED system that consists of 10 to 25 LEDs for headlighting. But as we go on to have more and more LED components in the headlighting, there will be interesting applications that will be popping up because there's basically more light to play around with. For example, over here, you can see that, hey, because of this digitalized lighting possibility, we can still light the road and turn off some LEDs such that when cars coming in, that we don't blind them. Uh, and that's basically one of the strong demand in the automotive industry that a lot of our automotive customers envision going forward, that the headlighting part is going to be digitized, and they want to add a lot of more functionality. It's not just for lighting the road. And to do that, we really need to consider of having also micro LEDs in our head lighting system. Now, for example, there is very a complex requirement of head lighting functions that one typically have in lighting the road that a lot of people probably never thought about. It's just turning on the lights and boom, there you can see some stuff on the road. But there is some requirements, for example, that some light is lighting the whole foreground over here, and some light only lights this part of the road and not so much this part of the road to avoid blinding people. And there is of course, sometimes you want to look further with the high beam of a road, and there is essentially the standardized area that the automotive industry typically looks when lighting a road can be divided by this 5 sections over here: a foreground section, uh, low beam cutoff, and a little bit of the spread, and then the high beam range and the high beam spread. And so, and we basically in Lumileds will try to provide products. We compete basically with every other major LED industry in the world to essentially provide a lighting system that is digitizing this whole thing. And so instead of just, okay, dealing this with 5 region over here, we essentially have an emitter system that digitize a more finer grid. And with this more finer grid digitization, we basically hope to offer functionality. And this is a picture of a demonstrator um, of the possible lighting system in cars that we have in mind in the future. A simple one LED which illuminate the whole foreground, and a matrix LED that covers more to the some areas, but more with less discretization, and the micro LEDs to cover more of the fine areas to add more functionalities over here. And for example, the uh, main foreground model essentially lights everything in the foreground, and the micro LED have this other digitization over here, and the ADB provide functionality for the high beam light and digitization of different regions essentially, but not as fine as the micro LEDs. And all have their functionalities. For example, in this case, when you have a curve on the road, hey, sometimes there could be some animals over here, and essentially with with this micro LED and ADB system, we can help warn the driver by identifying, hey, there is something to the side, and we envision a future in which the car itself can project these kind of signs for the driver to see, that they can react to it better, instead of having just a sign somewhere on the road that sometimes the driver ignore. If the sign is directly being output by the car, it's could help improve safety essentially. And this is a one of a possible usage of it in a dark setting of a country road, and there is a high beam that basically illuminates the hole further, and make things brighter and make things clear for the cars passing by this road. And some yeah, soft. And then when there is an upcoming traffic over here, the with the this digitized beam system, we can essentially help reduce amount of accidents by reducing the glare that this incoming driver sees because of the lighting, by turning off some of the ADB and micro LED lighting that in our headlamp. So that's basically a vision of how it would look like when there's a road. And you can see over here, this is an example of what the ADB system looks like. It's just a pair of squares over here, which is basically an LED chip with the yellow stuff is essentially the phosphor on top. That when you turn on the blue light coming from the LED, the phosphor converts it to yellow, and together they create a white light. And essentially, yeah, this is to show you that Lumileds recently demonstrated, hey, we can really pack this kind of high dense pixels in a micro LED system in a car lamp. Of, 20K pixels over here, and it's quite a decent lumen per pixel output of 0.4. We are trying to make it better and better, of course. And this is already at 85C operation. So keep in mind that there is also a digital challenge when making this kind of LEDs for car lamps, where you really have to manage the temperature. And sometimes LED efficiency essentially could decrease if you go to higher temperature. The IQE decrease. There is effect of phosphor quenching and all that, and you really want to maintain the temperature, but there will be problems, challenges that we still have to solve when considering micro LED structures that we are solving, and we are eager to have always interaction with academia and all that to solve that together with us. And this is a video of how this essentially we shoot our the demonstrator this tree system to the wall and show how things go. Just go into the wall, not on a car just yet, and see. Okay, this is the full illumination typically in a car lamp, and then as we go on, sometimes going to a curved road. You see over here, there is already white line being sent by the generated by the LED to help guide the driver. Okay, that there is really this road over here, and that could swivel, that basically help around the cars. And here is in the case when there is an incoming car with the sensor that is applied to the car as well, that it can detect, okay, there's some incoming car, so we have to kill some of the light and let the other light turn on. So, and some adaptive digitized beaming system. So that's first part of the advertisement of LEDs and Lumileds. I hope you all got excited about the future of your car lamps now, and got excited of Lumileds. But now more into the scientific part of what is actually needed in modeling the LED devices. By the way, going forward, if there's any question, just feel free to ask me. Um, now, LED devices. Um, you might be surprised how cheap they are right now, being sold one LED. Sometimes, depending on the LED, it could be just a few dollars, sometimes under $1. But the amount of physics coming into these devices is immense. Maybe because there's a huge amount of physics consideration, it could be made cheaper, but there's a really large amount of thought that needs to be put into in order to make a very efficient LED. Uh, First of all, when you design an LED for these different applications like lighting, home bulbs, and dev these devices that goes into car lamps, you first of all you have to consider what's a good geometrical model to model this thing as accurate as it can be, or you can make simplifications. Often, yeah, this is a step that a lot of people I think sometimes ignore. Yeah, just simplify everything, or just do the brute force, really include everything. This is also one of the first step, like meshing in uh, when doing numerical calculation. It's really important to consider how we can simplify things the first time. Do we really need to consider the whole actual structure, or we can simplify when modeling this by considering a simple structure that still well represent the device. And after we basically decide on a good CAD model to use in our modeling, then again, more of this fun start where we have to consider in LED calculations the electrical thermal portion of it, and how the electrical current spreading is in the LED model is. Basically, that determines very much a lot, and how the efficiency of this models will be, how we can inject the current, and where within the LED chip is the light being generated. Sometimes we want it to be evenly spread, sometimes we want it to be only concentrated in a particular uh, place over here. Uh, and sometimes, yeah, we want it towards the center, and sometimes it's on the edge. It's different applications and different models require different kind of um, current spreading possibilities, distribution, I mean. And and after that, I guess most of you are in the optics and photonics part. And then we start to consider how this electrical thermal could couple to the optics over here, and how they impact the optical performance. Of course, there's also the mechanical modeling that needs to be taken into account as well, and before we going on over here. But mm, uh, I can talk about that if somebody is more interested. But on the coupling to optics side, these electrical and thermal calculations often give us the information not only of how is the current spreading, so where the emission happens, but also what is the IQE of our emitters. Typically, in our products, we use quantum well emitters, by the way. Quantum well gallium nitride, and also in we have ion gap devices as well, and we use quantum wells. We don't really use quantum dots right now, but these quantum well emitters, as you probably know, most of you probably know, it's it's going to depend a lot on different things. Their IQE, the current injection level, the temperature, and uh, we have to take all this into account if we want to have a good model, because yeah, sometimes people say there is a good outcoupling of the light, but in fact there's going to be quite still a lot of bounces of the light, and they can be reabsorbed by the quantum well and re-emit it, and we have to take into account these things in our model. And to do that, we really have to have a good model that represents the electric and the coupling of the electrical to the optic side. And we the optic side basically is divided also into two, the ray optic side and also the wave optic side, because we want to basically take advantage of both structure. The LED devices that we have over here is it's multi-scale. There's components that are needs to be modeled with geometrical optics, and a portion of the interaction of the light needs to be modeled with wave optics. So for example, the emission of the light from the quantum wells inside of our gallium nitride epi, they're typically placed on the mirror, and we at least have to take into account, okay, the effect of the Bragg interference to calculate what's the Purcell factor over there, and estimate what's the angular radiation within this epi. And then after that, we do the ray tracing calculation and see how it interacts with other things like the phosphor, like the lenses, like the microtextures in the LED. So it requires a multiphysics modeling approach. And to demonstrate the multiphysics nature of this thing, like, let's say we show over here what we do typically in our automotive micro LED architecture when we model this. So this is typically one of our current consideration for the micro LEDs, which if you zoom in for each pixel is have a lot of complexities. There's a phosphor, there's the epi system over here, and there's also the interconnect over here, and there's CMOS backplane. And when we model these things to get the final light output, how much of the flux for a typical current injection, we have to consider, okay, what's the, when we inject a certain current from this side, how does it translate to the current spreading in our micro LEDs? And we have to calculate the voltages spread in this system. We do it with COMSOL, and of course we have to also consider, hey, what's the temperature distribution in this system to determine whether we are still good temperature-wise, or do we have to take into account to modify the system to have a better heat sink or things, and determine, okay, which IQE data we should use depending on the temperature. And then after that, there's additionally the complexity from modeling the emission from here, which requires a mix of wave optics and ray optics, of course. And it's really a multi-scale problem because these phosphorus layers of ours, depending on the applications in our typical products right now for headlamps, it's quite thick, several hundreds of micrometers. But we want to make it thinner, of course. Making it thinner would be better long run, because then the light will not have less time to interact with the edges, because the edge of typically would result to losses, because there is going to be at the edge, it depends in a micro LED system. If there are different approaches that we are considering, whether we want to really singulate each pixel or leave the phosphor to be film to be continuous. But if we singulate the pixel, which is provide better contrast and more functionality possibility in the road, better digitalization of the beam, we pay the price that, hey, some light can hit the edges of the singulated pixels and may be lost, or being scattered in a way that we don't want it to be scattered. And also, and here's a picture of one of our alien gap vertical thin film dye LED for that emits in the red. Basically, you can use it for the red signaling of the car, for your brakes and guided strips like here. And it's this system consists of a lot of layers of different semiconductor layers, and we show over here the complexity of our LED system, where there is the epi layer over here, which is actually consisting quite a lot of layers before the quantum wells. And there is components like this top over here is the end contact, the top contact over here, and this is essentially the mirror structure. And these dots over here you see here are the what we call them as vias, EVS, that injects current at these different positions into the quantum wells of this red layer over here. So it's a complex system that one might think that, hey, how on earth are we going to model this properly and optimize it afterwards? And because if you were going to model the whole 3D in COMSOL, hey, good luck. You won't be able to. I mean, using a supercomputer somewhere, it's nice and all, but it'll take too long to give to spit out a suggestion for a product. So we have to simplify matters when we model these things, and instead of doing the brute force of 3D, what we typically do is model them as a 2.5D system, which is our essentially interconnected sheet layers. It's probably one of the a lot of people do this in modeling current spreading and carrier transport. And instead of really calculating the current distribution, this complex 3D case, we just split them into two half-D layers that are interconnected with each other through a certain rate equations. So by doing so, we simplify greatly the problem. In COMSOL, it's if you have some experience, it's basically called basically using this layered shells technique. Although with the current release of COMSOL, I think they renamed this to something else. But when we use it, we call it just make some layered shell approach to the geometry. So we changed this 3D system over here for the alien gap case into this simplified flat surfaces over here that are coupled together with some coupling equations that basically govern how the injection at the different positions. For example, if there is injection from the dots over here, there will be only coupling terms on the dots. And from that, you basically could get this kind of a distribution of the here already the irradiance of the light. So from COMSOL, we basically calculate what's the current spreading would be in the quantum wells, and that basically could be related. Hey, when we measure the irradiance on top, this what we will see where the light will be coming out from. And you see over here there is some dark regions over here. That's because of the end contact. And this is an example of how we need to model the electrothermal optic case in some of our LEDs. So this is an example of an LED with a dome additionally to it, where there is blue light being emitted from the epi layer, and then we have over here a sapphire substrate, which is patterned also to provide the microtexture. So Currently, we rely quite a lot on our microtexture to improve light extraction from here. And then in this particular LED model, we have a phosphor coating all over, which converts the outcoupled blue lights into yellow light. And then there is this additional dome to help the extraction. Which is the extraction is just because this is with a certain refractive index of typically close to silica, a silica dome, and the dome shape allow light to outcouple more easy to air. And you can see over here already that it's a lot of different multi-scale problem. Over here from the emission from the quantum wells is the wave optics regime. And the simplified case of there's just a mirror. These days, we are actually one of the first companies that started to integrate nanophotonics in our LEDs. At least at TEMP, we had recently a grant given to us by the Dutch government to collaborate with the TU Eindhoven to be able to use integrate nanophotonics to improve the LEDs by integrating some nanostructures in different places in the LEDs to see how they impact the total flux and how they shape the radiation. And then, of course, in this case, where was I? There is microtexture over here that one can say that how are you going to model a microtexture? Or microtexture, unfortunately, it's a lie in those in between range. Sometimes that, you could say it's still okay with ray optics, but it's the size. You can argue that there is still some wave optics effect also over there, and we have. We'll show later that we actually have to model it better if we model it better. In some cases with wave optics consideration there, and but we have to couple it with the ray optics tool afterwards. And when modeling this, for example, we have to consider as well that in this system heat could be a problem because of the possible phosphor quenching effect, and we have to take into account when we model this in order to know in the optical model which efficiency we have to assume for the phosphor when the light is absorbed and to be re-emitted. And we do that by doing the electrothermal calculations to see a coupled optic and thermal calculation to see how much is the phosphor temperature and what's the spread of the temperature, and whether that also helps us optimize whether we have to better think of a better tile or a grid system in which we place these LEDs in order to spread the heat better. Because as you can see over here, this is a typical plot of what we get when for a phosphor performance for 3 different temperatures. As you go, this is essentially the PCE, and you can see that the irradiance basically goes down as a function of the temperature. And also, if you have more blue light being absorbed in the phosphor, there'll be some phosphor quenching effect, and we have to take into account that also some blue light irradiance can impact how efficient a phosphor would emit yellow light. And all this needs to be taken into account when we design this thing, so we can really optimize the whole problem to provide an LED device at the end that it would be functional enough for the customer to use. This is basically us showing that we do this multi-physics modeling, and we always calibrate it, of course, with experiments. And in Lumileds, we already have this knowledge base to be able to do this well and to be able to match experiments well. And this is a slide describing of what we typically have to do optics-wise. There is a emission, of course, just a simple emission of dipoles on top of a reflector over here that we have to consider. But then we have to take into account that on top over here, these triangles are typically our microtextures. Our microtextures on the pattern sapphire substrate to help the outcoupling. Yeah, our microtexture looks very, very strange. It's one of those things where asymmetry actually helps. I mean, there's still some symmetry in the placement of these things, but the asymmetry of the object, we saw that it actually benefits in inducing more light outcoupling. And we typically, instead of just relying on a ray optics approach over here, sometimes depending on the material system, we have to take into account the wave optic scattering effect, because these microtextures really only is several microns sometimes in diameter on the base of this semi-pyramid, I suppose. And there could be some interesting diffraction effects that, if we don't take into account, actually would give us would lead us to underestimate the outcoupling potential of these structures. And of course, after that, what we typically do is, okay, we model this the scattering properties of this microtexture by simulating just incoming plane wave at different incidents to this structure. And basically we collect all the scattering response, all the diffraction orders for incoming plane wave, incoming at different directions, and we build ourselves a BSDF data that we feed to our light tools ray optics solver, so we can model the entire system, and then we can trace how the ray goes into the phosphor and interact with different other objects within the LED system. So as you can see, to conclude on this part, what is needed in an industrial LED modeling, first of all, it's quite time consuming to build this whole thing together. So we rely quite a lot in building our LED models in automation because in the past, actually just around 5 years or 10 years ago, a lot of people, a lot of engineers over here are still making those CAD model and the COMSOL model almost manually. It's very tiresome. And that really limits the speed in our ability to go to the next product. And we need automation, and basically, and we need the ability to process complex geometry in our calculation by simplifying things, and also a multi-scale device physics model. And of course, we have to consider computational efficiency when we decrease this, because we don't want to just, oftentimes we need to get our results of modeling within a few weeks or days, not months. And also, yeah, we need to improve the throughput of this development in a timely manner. So that's basically the main thing that I wanted to talk about. And I just wanted to say also as well that right now there is an opening in Lumileds for device architecture scientists in our branch, our main branch in San Jose. But we're basically looking for mainly for a PhD in optics, physics, photonics, electrical engineering. But this opening is closing soon, so if some of you are interested, please give the application soon. You can just Google device architecture scientist Lumileds, and the advertisement will pop up. If not, feel free to contact me, then I'll forward you to it. And then also we plan internships to establish collaboration with the universities, and there will be another internship topic coming on next year on optimizing photoluminescent high brightness LEDs. And just keep it in mind for those master thesis students that might be interested to do an internship next year. We already thankfully getting 2 internship students from Ghent this year, starting in September. So we're looking forward to have more students from Ghent University. And that's it from me. Hello?
Okay, thank you. So I think we can now go to the question section. So I don't know if people have questions. You can raise a hand and ask your questions.
And there is a question in the
Yes.
chat box from Dennis. Dennis, do you want to ask it yourself?
Okay, yeah, so I was wondering, you were talking about these LEDs that you can dim them if you have an oncoming car, but doesn't it need to be the other way around, that you actually see this car and you increase the brightness of the LEDs?
Huh. I mean, interesting thought. But if you increase the brightness of LEDs,